Hi guys, this video should hopefully not be too long, and in it I'm going to give some background and intuition that will be useful before we launch into the pumping theorem for context-free languages. So the three things that I'll need you to remember before we start this video are what the basis for the pumping theorem was for regular languages, and that was that we said that if we had a long string that was regular, then it must go through a cycle somewhere in any FSM that can accept that language. Also remember what a context-free language is, and in particular what parse trees are. So if you're still struggling a little with parse trees, go back over those notes before we jump in here. So some notes on trees in general before we start. If we have a tree where non-leaf nodes are expanding, and then we eventually get down to leaf nodes, which are nodes which do not have children, the branching factor of that tree is the largest expansion from any non-leaf node. So in this case, the branching factor of this tree is 2, because these two expansions are of size 2. But if I added this expansion here, it would be of size 3. And if I added this, the branching factor would be then 4. The height of a tree is simply the longest path from any leaf node to the root node. So in this case, the height of this tree is 2. But if I added these nodes here, then the height of the tree would become 3. So one of the key things that we can note is that there is a bound on this number of leaf nodes in a tree, which has branching factor B and height H, and that is that the number of leaf nodes here, which I'm going to call L, is bounded by the branching factor to the power of the height of the tree. So there is an inductive proof that we can do for this, but I'm not going to do it here for the sake of time, but keep that in mind. So we know from our parse trees that everything that is a leaf in a parse tree must form part of a string, and therefore must be an element of sigma. Now, we also know that every time we have a node and we expand it into other nodes, then that must be a valid rule in the grammar. Now, that must mean that the node that we have expanded forms an element of the non-terminals, since our rules for context-free grammars say that we can only have non-terminals on the left-hand side. So what that means is that every non-leaf node in any parse tree must be a non-terminal. Now, let's say that we have a grammar here where I have non-terminals going into some set of terminals and non-terminals. The branching factor of any parse tree corresponding to that will be at most the size of the biggest rule in the grammar. Because the branching factor, remember, is the biggest expansion of any node into other nodes in the tree, and the biggest way in which we can have such an expansion corresponds to the biggest rule in the grammar. So in this case, the branching factor of any parse tree generated by this little grammar here can be at most 6. What that means is that we have a bound for our branching factor for our parse tree, and that is based on the biggest rule in the grammar, but nonetheless it's constant for any grammar. And we also have a bound for the height of a tree if we don't reuse any non-terminals. So let's say we've got a grammar and we've tried to produce a string without reusing any non-terminals, then the height of that tree is bounded by the size of the set of non-terminals. Now that's important because that means that we said before that we had a limit on the number of leaf nodes that we could have in a tree with a particular branching factor and height. So now we have a limit for the size of a string that can be generated by any grammar without reusing rules. So let's say that we've got, in this case, we know that the size of the number of leaves in this tree is bounded by the branching factor to the power of the height. Now in this case what that means is that it is bounded by the branching factor, which is the size of the biggest rule, to the power of the number of non-terminals, if we don't repeat. And that is a bound on the size of any string that can be generated without repeating rules from the grammar. So let's recap what we just said there. We just said that if we have a parse tree which does not reuse rules from the grammar, then we have a limit on the size of the strings that can be generated by that in that case. And that is the length of the string is less than or equal to the branching factor to the power n, and in this case n is equal to the size of the set of non-terminals. And that's important because we're basically coming up with the same sort of thing as we did when we were talking about the regular languages. We said before that we have some bound on the size of a string that we can generate without going through cycles, i.e. repeating states in a finite state machine. Now, when we're talking about the context-free languages, we have a limit on the size of a string that we can get without repeatedly applying rules from the grammar. So we have the same thing, that unless we go through some sort of recursion, there is a limit to the size of the strings that we can generate, given any particular grammar. And that's important because that's what we're going to use to build up a pumping theorem for context-free languages, which is what we're going to be able to use to prove that languages are not context-free. So now we have a definition for what we mean by a long string for context-free languages when we're talking about the pumping theorem. That is, a long string is one which we have to expand a non-terminal more than once. So when we've got such a long string, then we can talk about the parse tree for that string. Now we know that there may be, even for a particular grammar and a particular string, there may be multiple parse trees. What we're going to say is we're going to reason about the parse tree, which is the smallest one. That is the one with the least nodes in it. Secondly, all we know is that we have to have repeated a non-terminal at least once, but we could have repeated another non-terminal at least once, or we could have repeated multiple non-terminals multiple times. But when we reason about the tree, we're going to pick a point where we have expanded a non-terminal twice, and we're going to say that we pick those points such that there is, below this point here, there are no other non-terminals which have been expanded more than once. Now we can do that because in any particular parse tree, there will always be finally be the last occurrence of a repetition of an expansion of a non-terminal, and we'll just pick and talk about those ones. So the key is that this parse tree that we've got here, where we assume that for a given string, long string, that this parse tree is general, i.e. because the string is long, there must be a repetition of an expansion of at least one non-terminal, and we're going to reason about the one that gets expanded last in a sense, i.e. there are no further ones below the first occurrence. And we're also going to say that the particular parse tree that we're reasoning about is the smallest one. So the other thing to note about the way that we've broken this parse tree up is that we have broken the string into 5 pieces. We've got U and Z, which are outside parts that are generated before we get to this expansion of X here. We've got V, X, Y, which is the inside part generated from the first expansion of X. And inside of that, we've got X here, which is generated from the inside of the expansion. So what we have is that W equals U, V, X, Y, Z. And each of those are substrings. They're not symbols in the language, they are substrings. We can make a few observations from this, and that is, we expanded X here and then here again, but because they're the same non-terminal, we could have just done the expansion here, up here, and then we would never have gotten the V and Y. So that means that this statement is true, that U, X, Z must be a string in the language. We also know that when we get down here to X2, we could have used the same expansion that we did before at 1. So we could have done that again and then come down to another X2. What that means is that we can shove a v and a y in between vx and xy. And we can do that as many times as we want. So that means that these two statements are true, that u, v, v, x, y, y, z is in L, or indeed u followed by any multiples of v, followed by x, followed by any multiples of y, followed by z, must be in the language generated by this grammar. So this is what we mean when we talk about pumping in the context-free sense. So in the regular sense, we had this little one bit that we started pumping. And here we've got two bits that we pump in concert. There are a couple of things that are important to remember. And that is that the rule that we expanded here may have been something like x goes to axb, but it also may have been a one-sided rule, like ax or x goes to xb. So what that means is that this could be empty or this could be empty. The reason that they can't both be empty is the fact that we stated before, which was that this is the smallest parse tree that can generate it. Now if v and y are both empty, then the parse tree which doesn't include x1 at all could also validly generate w. So that means that at least v or y, one of them must have at least one symbol in it. So either of them can be empty, but they can't both be empty. Now another thing is that we said that when we expanded x1 further down, there were no repetitions of any rules, any non-terminals from that point further down. What that means is that we have a bound for the height of the subtree from x1 further down. And it's the same rules that it's the same bound that we talked about before. If we're not repeating any non-terminals here, then the longest possible chain of nodes that we can have is limited by the size of the number of non-terminals. So if n is this case, then including x1, the maximum height of the tree rooted at 1 is n plus 1. That's because there is one repetition of x and 1, but there are no more repetitions further on. What that means is that we have a bound for the size of the middle part of this string, which is that it is no longer than the branching factor for this particular grammar to the power of n plus 1, where n is the number of non-terminals. So that's important. We can break the string up into these 5 parts, and we know that at least one of these 2 parts is not empty, and we know that this middle section here is bounded in length. It's starting to look like it's something very similar to the pumping theorem that we had for regular languages. So what we arrive at is exactly that, a pumping theorem, but for context-free languages. And it says, for all long strings, that's all that first line is saying, we can break it up into 5 parts, u, v, x, y, z, that's all that's saying, where v and y are not both empty, so at least one of them has characters in it, and where the middle part of the string, v, x, y, is no longer than k, so it's bounded in size by k, then all of the strings that can be generated by repeatedly pumping in v and y at the same time, or pumping them both out once, are in L. So, u, x, z is in L, u, v, v, y, u, v, v, x, y, y, z is in L, etc. So what we can do is we can take this as a true statement about all context-free languages, and then we can say, if we are given a language that we think is not regular, we can say, well, if it was, not context-free, if it was context-free, then it would obey this property, and then we prove that it doesn't obey this property, and by doing so, we have proven that the language cannot be context-free, in the exact same way that we did for the regular languages. So the overarching proof style is completely the same for this as it is for the regular languages, but what we have is that the actual mechanics of the proof are a little bit more complicated because we have these larger string parts and we have to pump things at the same time. And unfortunately, this bit that's bounded in length here in the middle is not at the start or the end of the string. And you'll see later that that makes the pumping theorem proofs for the context-free languages quite a bit more complicated than for the regular languages. So that turned out to be a little bit longer than I'd planned, but what you should now know is how we get to the pumping theorem for context-free languages. And if you're a little bit confused, you can go and look at section 13.3 in the textbook, which basically goes through everything that I just went through there, possibly in a slightly better explanation.